Hello, this is problem set number 5, problem 7. A semicircular plastic wire of radius r has a uniform linear charge density lambda. A point charge q is placed at the center of the semicircle. What force does it feel? Give the magnitude and direction. So I drew the semicircular plastic wire of radius r here. And the center of this semicircular plastic wire is the origin, right? And it has a radius r, as seen here. Okay. So now I'm going to place a point charge of q right at the center or at the origin. And this has a charge of q, right? So now let's try to find the force that it feels. I'll admit that I'm a little confused by the question because it does state that the semicircular wire has a uniform linear charge density that we're calling lambda. But I don't know if the charge is positive or negative on the wire, on the semicircular wire. So that confuses me a little bit. And that's just a heads up. So I'll try to answer this to the best of my ability, but I'm not too sure if my answer is going to be correct. Okay. So I'm going to use Coulomb's law for electrostatic force on Q to find to try to find the answer to this problem. And the Coulomb's law states that F on Q, this is electrostatic force on Q, actually I'll write the definitions later, is equal to so F on Q is equal to the point charge times the electric field at location Q, okay? And that could be rewritten as Q, and the electric field is just the electrostatic constant K times Q1, which is the source charge, over R squared. And R is the distance between charges, okay? And so now I'll kind of explain this here. So this is the electrostatic or electric force, right? Electrostatic force on Q. This Q right here, this is the point charge. Okay. This Q right here, that is the source charge. Okay. And in this problem, the source is this semicircular plastic wire. K, that is just the electrostatic constant, so I won't bother with that. And R is the distance between center of charges. All right. I could actually rewrite this still even further if I wanted to, since K is equal to 1 over 4 pi epsilon naught. So that would be Q times 1, or sorry, that would be equal to Q divided by 4 pi epsilon naught times Q1, which is a source charge, and over R squared, okay? Oh, sorry. In this case, our radius is capital R squared, right? Okay, so that is our force. Okay, electric force for this problem. All right. What about if I wanted to break this semicircular plastic wire into little chunks right here of, I'm going to call this little chunk of charge D. Oops. I'm going to call this D Q. All right. And DQ has a certain length right here, arc length of ds, and that is a certain d theta, okay? That has a certain angle for that segment of arc length, small segment of arc length. Okay. Let me just make this clearer that that's going to the origin. Okay. So if, let's use our arc length formula. So S, that's a total arc length, S, is equal to, by the way, this is a total arc length right here, from here to here, this whole thing, that length right here. So if that is equal to r, since that's a radius, times theta, whatever our angle is, then our little segment has a length of ds is equal to, it's still going to be r because it has the same radius, right? From here to here. It's a semicircle, so it's still r. And instead of theta, now we have this little chunk right here of d theta. All right. And I'll put a little cloud around it so I could remember that later. Now remember our semicircular wire has a linear charge density. So this was arc length. Now this is a linear charge density. Which is lambda equals the total charge of the semicircular wire divided by the total length, right? Which actually we call that S, right? That's the arc length, total arc length. Okay? So if that's the case, then Q, or the total charge, would be equal to the linear charge density times the arc length, okay? But that's total. These are total charge, or linear charge density, which is a constant, right? Whether you're talking about a small segment or the entire semicircular wire. And this is the total length of the semicircular wire, S. That's the arc length. Okay? So, if that's the case, then this little dq, this little charge I have right here, it's going to have a small charge of dq, right? And that's going to be equal to lambda, because the linear charge density is constant, ds, okay? And remember, ds is just r d theta, so I'm just going to plug that right in. So dq is equal to lambda r d theta, okay? I'm going to put a little red cloud around it so I remember to look back at that. Okay. So now going back to my formula for electrostatic constant, or electrostatic force, I'm sorry, right here, right? where Q1 was my source charge, or the charge for this entire thing, right? I'm going to break this down instead of the entire electric, or the entire force felt by particle Q. I'm going to break it down into just this little dF, or this little force felt due to this small segment, okay? And remember, in this entire semicircular wire, we have an infinite number of small segments, right? And we just have to add them on top of each other. Okay, so my dF is going to be equal to Q, which is my point charge, over 4 pi epsilon naught, right? That's just K. I'm basically copying this, by the way. And instead of Q1, remember Q1, this is the source charge for this whole thing. I don't want that whole thing right now. I just want this tiny thing. So instead of Q1, I'm just going to put dQ. That's just the charge for this tiny segment. And I'll divide that by the radius, which is r squared, right? Okay. And now I'll substitute my dq here for the dq that I've solved for here. So that would be equal to q over 4 pi epsilon naught over r squared times pi r d theta. Okay, so I can cancel some stuff out. This r cancels with this square. All right, and I am left with my df is equal to q lambda over 4 pi epsilon naught r d theta. Okay, so I'll put a cloud around that. So let's take a look at our picture real quick. Do you notice that this is symmetric, meaning that this part is symmetric to this other half, right? So whatever, let's say we have a certain force due to this charge going this way, we're also going to have a certain force from this charge, and that one is going to go this way, right? And these two forces have an x component and a y component, right? But the y components, let's say they're both the same angle, theta. The y components are equal and opposite, so they're going to cancel each other out. But the x components, they're going to add on top of each other, right? So with that being said, due to symmetry, the y components of force are equal in magnitude but opposite in directions, so therefore they cancel out. Okay, so right away that's something we would notice, hopefully, is that notice y components of force are equal in magnitude but opposite in direction. Due to symmetry. Therefore, they cancel each other out. And so df and the y component of df is equal to 0. All right? That is our first, that's our first half of the answer, right? That's the force it felt and the magnitude. Magnitude is along y, or the direction is along y, the magnitude is 0, okay? Now, let's look at, sorry, not df, but actually that would be Fy. The force along the electric force along y would be 0. Because all the df's here, this df would cancel with this df, y, right? The y components, they cancel out. If let's say this, and then this and this, the y's cancel each other out because they have the same angle and it's symmetric. Okay? And then notice that for x, because it's all in this half of in the second and third quadrant of this graph, the x's are all going to stack up on top of each other, right? They're all going to face this way towards positive x. Okay, so they're going to stack up, or it's going to face there if the charge of this semicircular rod is also positive. It's going to face towards positive x. They all stack up on each other. But if the charge of this semicircular rod is negative, then they would all stack up towards negative x, right? So df x is going to be equal to if let's say let's pretend that the charge on the semicircular rod is positive, so it would push it out here, right? Or I guess for this dq, it would push it there in that direction, right? And if this is theta, then this is theta. Okay, so dfx would be df cosine theta, right? This x component would be df cosine theta. All right. That's going to be df times cosine theta. And df is equal to q lambda over 4 pi epsilon naught r, and then times cosine theta d theta, right? And that would be our tiny force felt by particle q because of this tiny segment of dq, right? This guy right here. But what if I want to add all of it together to go get the force felt at q at the point by the point charge for the entire semicircular wire? I would have to integrate in order to add these little dq's together, right? That way I would be able to add this little segment plus this little segment, the forces felt by every single segment until I go through this entire wire, okay? So I'm going to do that. And that would be fx is equal to the integral of dfx, right? And because our angles here is pi over 2, right? It starts at pi over 2, or maybe it starts at 3 pi over 2 and ends at pi over 2. But anyways, we go from this angle to this angle, right? So I will say that this is equal to, and I'm going to take out the constants of dfx outside of the integral to make it easier on myself. So q lambda over 4 pi epsilon naught r times the integral of cosine theta d theta from, let's say, from 3 pi over 2 to pi over 2. Okay, since that's the angles. So from 3 pi over 2 to pi over 2. And then I would get that the answer is q lambda over 4 pi epsilon naught r. And the integral of cosine is sine theta. 3 pi over 2 to pi over 2. And that is equal to q lambda over 4 pi epsilon naught r times sine of pi over 2 minus sine 3 pi over 2. Right, and this becomes sine pi over 2 is 1, sine 3 pi over 2 is minus 1. So then that becomes, what's in there becomes 1 minus minus 1, or 2, right? So then I would get 2q lambda over 4 pi epsilon naught r, and I can cancel out the 2 and 4. So my final answer would be fx is equal to q lambda over 2 pi epsilon naught r. And that would be my final answer for the force felt by point charge q. Okay, and I guess to make this a vector, I'll just add a direction. So that's I hat, okay? And like we said, for y hat, that's 0 because they cancel each other out. So I think that's how you answer this problem. I'm not sure. Again, I was confused because I didn't understand if this semicircular plastic wire of radius r, if that had a positive charge or a negative charge. I understood that the linear charge density is lambda and that it's uniform, but I'm not sure if the charge here is positive or negative. So I'm a little confused by this problem, but hopefully the concept did help understand this.